Hello, we're going to talk today about chemical kinetics, which is chapter 14 or note set 14 if you're following along in the notes, which I strongly suggest. Kinetics is the study of rate, how fast it takes a reaction to proceed. This is different than thermo. Thermo is basically telling you, in a sense, your destination. Thermo tells you your composition that you're ultimately going to have when a system, for example, comes to equilibrium, about the energetics of the system. Kinetics is a study that's dedicated to the speed of a reaction, how quick a reaction proceeds. And that can vary over many orders of magnitude. Some reactions are exceedingly quick. Other reactions take place on geological time scales. So let's make some, just right now, we're just going to do an introduction to the notes. I'm going to follow the notes roughly. Kinetics is a study of rates of reaction. The big idea here is we're studying how fast reactions go. We're studying rates. Some of the factors that can broadly affect rates, and we'll study these in detail as we move along, is concentration of the reactant species. So if you have a reaction with different chemical species, their concentrations will matter. The temperature. Usually reactions go quicker at higher temperatures. There are some exceptions to that. The structure and the orientation of the molecules that you're dealing with can be a factor as well. So all of these things we'll study in more detail, but first I just want to lay out some of the structural features of how we set the math up and the equations that we'll use. This subject itself is often taught with calculus. This is not a calculus-based course. As we move along, a lot of the topics I'll have to put equations up that I'll explain conceptually that come directly from calculus. If you do know calculus, in the back of my skill builder, I do have an FYI where certain features, certain equations come from, so you can look at that. And if not, that's totally fine. You can understand this material without it. So if we think about rate, we deal with rate all the time. When you're driving, you have speed, which is really a measure of a rate, right? So if you think about speed, what is speed? Speed's a change in distance, and I'm using here the symbol delta, to triangle, just to mean change in distance, how far you go, over the change in time. Over the change in time. So when we're dealing with chemistry, we're not dealing with distances per se, not physical distances, but we're dealing with reaction systems. So let's take a reaction system of H2 gas plus I2 gas going to 2HI. Everything's in the gas phase. I really don't even have to write that in. Let's take some of the species here and think about their rates. Now, one of the conventions is we want the rate to always be reported as a positive value. So when we write, for example, if we want the rate for, let's say, hydrogen, we can think about it as the change in the amount of H2. I'm just putting the bracket here to represent concentration. And you could actually do this with partial pressures as well. We're not going to do that right now. Over the change in time. So the H2 is a reactant. By convention, we write the reactants on the left, the products on the right. The one correction you have to make to this, let's look at this in a little detail. This is actually going to be, you're going forward in time, so we'll say it's T2 minus T1, a later time minus an initial time. And the concentrations will be H2 at time 2 minus H2 at time 1. I'm just using the subscripts here to represent, that this is later and this is earlier in the reaction. Now, look at this. T2, that could be 10 seconds, this could be 1 second. That's positive, but hydrogen is decreasing over time, so the top is negative. So we have to correct for this just by convention. We want to report this as a positive value, we have to have a negative sign in front. We have to have a negative sign in front to correct for the fact that we have a negative in the numerator, positive in the denominator, overall negative. We want to make it positive. So for your reactant species, you have to build in a negative sign in front of the equation. I have to erase above here. For I2, it's similar. For I2, so we put the negative in here for emphasis. For I2, you're going to have be the same way. It's going to be negative the change in I2 over the change in time. Which, if you want to see it all the way out, that's going to be negative. I'll put a little bracket up here. I2 at time 2 minus I2 earlier on. 1 over T2 minus T1. For the HI, it's increasing over time. So the rate is going to be equal to the change in HI over the change in T, except we want to have a common number for the rate. So what we have to do is we don't have a negative in this case, but we divide it by a 1/2 to adjust for the fact that every time you lose an H2, you form 2HI. Every time you lose one I2, you form 2HI. We adjust for that but we leave it positive, but we have to divide by 1/2. And so this would be physically equal to 1/2 times HI at time 2 minus HI at time 1 over T2 minus T1. So those are expressions of the rate. We can write this in general, so let everybody get a clear view of that. We can write a generalized form of a reaction where this lowercase a, b, c, and d are stoichiometric coefficients for a balanced equation, and the capital letters a, b, c, and d can represent the actual chemical species of interest, atoms, ions, molecules, what have you. So we can write for this expression, the rate, I'm just going to call rate R, is equal to, for this left-hand species, we have a negative sign in here, 1 over A. Now, sometimes A could just be a 1. The change in A over delta T, the change in T. And if you know calculus, these would just be derivatives, but if you don't, that's fine. We'll just write the triangle. And then for B, 1 over B is equal to change in B, change in T. I'm going to continue it below it. That's going to be equal to positive 1 over C. And if you want to put the positive sign here for emphasis, and this is the little c here, it's hard to tell the scale, I'll make it a little littler. Change in C, change in T. So these are, again, the negative signs here in the numerator, and the ones in the top are basically making this positive. These are already positive. We don't have to do that. We just have to adjust for the stoichiometric coefficient. 1 over D, change in D, species D, whatever it is, change in T. So this is just giving you a concept of what rate is. What we're going to move on to next time is some of the different ways we can describe rates, and I'll talk about the deficiencies of them, because there's one of the problems with chemical reactions, as you'll find out if you take orgo and biochem, is that there's a lot of competing inside reactions as reactions progress. there's problems in terms of interpreting the data because you have a lot of things going on. So we tend to want to look at reactions very early in the reaction process. So we tend to present things in general chemistry because your learning subject is idealized, but in reality, most kinetic studies are done early stages of the reaction if we can do it. So we'll talk about that next time, and then this is actually a really good, interesting chapter. So on that note, hopefully make another video later today. Take care.